Until now, we have tried to analyze thermodynamic systems using the conservation of mass principle, the conservation of energy principle, the first law of thermodynamics. We've looked at closed systems, we've looked at controlled volumes, but usually that's not enough to analyze thermodynamic systems. We need um, another law, which is called the second law of thermodynamics. And why we need it? Well, there's different reasons for it, and I'm just going to go through them really quickly. So obviously, we've discussed this before that every process has a direction, and then there's something called spontaneous processes that take place in nature. So with spontaneous processes, we have processes taking place that go towards the equilibrium state. So, for example, an ice cube melting and becoming or turning into a liquid, that's a spontaneous process. And now there's a definite direction for these spontaneous processes, but um, the first law of thermodynamics or the conservation of energy principle, they cannot predict this direction of the process. So, for example, the ice cube example, ice cube turning into a liquid, that is something that we know intuitively. We know that that is something that would happen, but let's say if we did not have intuition, then based on the laws, first law of thermodynamics is not enough to define that direction because I could, let's say, analyze the energy changes that are taking place of this conversion of the ice cube into liquid water. I could look at the energy changes, but this first law is not going to tell me the direction of the process that ice cube is being converted into water and water is not being converted into an ice cube. So to in order for me to get the direction of the process, that's why I need the second law of thermodynamics. So I'm just going to give you another example related to that. And this is, let's say, a body. This is a hot body which is placed in surroundings, and the surrounding is atmospheric air. The body's at a higher temperature, that's why it's a hotter body. And over time, what I know is that to try and reach the equilibrium state, because this body's hotter, the air around it is colder, so you could consider this like, let's say, a coffee mug, right? And now this coffee over time is going to try and get colder and try and attain the same temperature as that of the surrounding air. That is what happens over time, and that is what we know intuitively. And this is the spontaneous process that is taking place. So, uh, the energy changes that are taking place, the energy is conserved, obviously, but uh, if I wanted to, let's say, go in the inverse direction of this process, now this is a spontaneous process. The inverse of this would not be a spontaneous process. And what that means is that this body that is a colder body now will not get hotter without, let's say, some kind of external system being attached to it, some auxiliary device attached to it. For example, a reheater, let's say. So just by itself, if this body is sitting here with atmospheric air around it, we know that the inverse of it cannot happen. Now, I could still apply the conservation of energy principle on the inverse process, and it would be completely fine. I could get some kind of values out of it by applying the conservation of energy principle. But would that be the correct way to go about it? So what that means is that every process that is consistent with the conservation of energy principle, it doesn't mean that that process can actually occur, right? So just because we can go ahead and perform an energy balance on some scenario does not mean that that process is can take place or that direction of process can take place, right? So to define what kind of processes can take place, we need the second law of thermodynamics. The second thing is um, that in a lot of cases, to approach equilibrium, equilibrium can be achieved quickly. It can be achieved a lot slower. So, for example, if ice is melting, it could take a couple of minutes to do that. At the same time, if let's say we have an iron bar, for the iron bar to rest away, it could take thousands of years, let's say, right? So whether the process is rapid, whether the process is slow, it will obviously satisfy the conservation of energy. But that by itself is not sufficient to determine the final equilibrium state that is being reached. And that is another thing that is provided by the second law of thermodynamics. Just like this example, if I had another example, let's say where I've got a tank which is filled with pressurized air, right? So I've got high pressure air in here, and let's say this is at a pressure PI, and I've got atmospheric pressure outside, which is P naught. So PI is greater than P naught. And if I allow this high pressure air inside to interact with the outside air, what that would mean is that I would let the air expand into the outside air, right? And the pressure of the air is going to reduce until the pressure inside the tank becomes equal to the pressure outside. So until the pressure inside is P naught as well. And that intuitively we know that this is a spontaneous process. This is the natural direction of the process. The inverse of this couldn't happen, right? Couldn't happen. That's not possible unless obviously we had some kind of external device attached to it where we were pressurizing the air, but then that means that we have to basically take energy from the surroundings and invest that into this tank now and increase that pressure. So by itself, just by this tank setting here with gas at pressure P naught, if I tried to increase the pressure by itself, that wouldn't happen. Direction is not possible. And again, just because of our previous experiences, we know that this is not possible. But let's say if we did not know, let's say if we had a more complex system, a lot more complex system, for which intuition couldn't play a role, for which our experience couldn't play a role, then we need a set of guidelines, right? Then we need some kind of law that would define this process for us, that would define the direction of the process for us. So that is why second law of thermodynamics is important. Another thing that we need to consider is that when we are letting, let's say, this gas expand, so we've got a high pressure air over here, and we're letting this gas expand, and if we let it expand just like that and let the pressure come down to P naught, then we're kind of wasting the energy that was within this high pressure energy, because this is an opportunity to develop work, right? Because instead of letting the air expand aimlessly into the low pressure surroundings, we could have just like passed this high pressure air through, let's say, a turbine, and then the turbine blades would move, and then the mechanical shaft attached to the turbine would move, and work could be developed. So that means that there was a possibility to develop work which could be exploited in a controlled manner. But if I let it expand, if I let this gas expand in an uncontrolled process, then I'm not really making use of that opportunity to develop work. Just like that, when I'm looking at this example, where I'm letting this body cool down spontaneously with no other result. Um, I could also let this body basically transfer its heat through a power cycle, let's say, and that could develop a net amount of work, let's say. So once again, uh, the body is obviously going to attain equilibrium by the end of it, but there's opportunity to develop work in there which can be utilized. So that is another thing that we need to consider. Uh, that the natural question should be that okay, if we can develop work out of these opportunities, then how much work can we develop out of it? So what that means is that what is the maximum value of work that could be obtained for any of these processes? Let's say I've shown you an example of two systems. There could be 1,000 other systems like this. So for these systems, what is the maximum value of work that I can get? Because obviously, we cannot have unlimited work, right? Because if we had unlimited work, then that means that if I just give you an example of, let's say, fossil fuel producing electricity, if we could have had unlimited amount of work, then we wouldn't need to worry about running out of those fossil fuels, right? But we have to keep on consuming those fossil fuels in order to keep developing work. So just a limited amount of fossil fuel, let's say 1 kilogram of fossil fuel, can only produce a certain amount of work, and that would be the maximum value of it. It cannot produce unlimited work. So that is the first question that we need to answer, that what is the theoretical maximum value for work that could be obtained. And I'm talking about theoretical maximum value because uh, the theoretical maximum value would be the idealized maximum value. In actuality, in real life processes, we need to account for factors like friction, let's say, uh, that would reduce the actual amount of work. So this is the maximum limit basically that can be achieved, but the actual processes would always have a lower uh, maximum value of work. And the second factor, then, this is what I'm talking about, that what are those factors that would basically be present and that would make sure that the maximum theoretical value is not being attained, right? So then with the second question, basically we come up with different factors like let's say friction, or it could be other factors like that that are present in actual systems, and based on those are the factors that would basically negate the realization of the maximum value of work. So it is also important to understand these factors, and then we can, if once we understand these factors, we can try and minimize that. So if we've got friction taking place, we can try and reduce that friction as much as possible to attain as much work as we can, right? Because we do not want to waste energy that we can use. So that's why it's important to keep on improving systems, to keep on uh, understanding these factors better, to keep on designing things in a way that these factors are reduced, right? So I'm just going to move on to the statements of the second law of thermodynamics. There's different alternative statements. We're going to just look at two frequently used statements called the QuasiA statement and the Kelvin Planck statement. And I'm just going to start off with the QuasiA statement first. And what the QuasiA statement says is um, that it would be impossible for any system to operate in a way that sole result would be an energy transfer by heat from a cooler to a hotter body. Now, this statement seems simple enough, but the important point in this statement is these words, sole result. What it says is that any system that is operating in a way where energy transfer is taking place by heat from a cooler body to a hotter body, that is not possible. Okay. If the system is operating in a way that the only way that it is interacting, the sole result is that the energy transfer is taking place from a cooler body to a hotter body. That is not possible. That is what the QuasiA statement says. And in a way, the QuasiA statement is telling us the direction of the process, the direction of the spontaneous process. So if, let's say, energy is being transferred from a hotter body to a cooler body, according to the QuasiA statement, that is possible. The opposite of it, that is not possible. And that is what we know by intuition as well, by our experience. So, QuasiA statement is easy enough to understand like that. It also implies that it is impossible, let's say, to construct a cycle. So it is impossible to basically construct, let's say, a refrigeration cycle that operates without an input at work. What does that mean? That in order for your refrigerator to run, you need to provide power to the refrigerator for it to cool down your food even further. It's not possible that this could happen. Like if you imagine that this is your refrigerator and you've got, let's say, food in here, and now this food, if you want to take energy content out of it, that means you're cooling this food further. And what QuasiA statement says is that it's not possible for you to cool this. It's not possible for you to take the heat content out of the system and transfer this heat content elsewhere without inputting some sort of energy through, let's say, work into the refrigerator first. So this is what the QuasiA statement is. This is the second point that I'm talking about, that heat transfer from a cooler to a hotter body is possible, but there must be some other effect that should also be taking place in the form of work. The second statement, which is the Kelvin-Planck statement, now we're going to just look at that. But before we look at the Kelvin-Planck statement, there is an important concept that we need to understand first, and it is called a thermal reservoir. And a thermal reservoir, or simply called a reservoir, is a special kind of idealized system. So it's an ideal system that remains at a constant temperature. So the temperature of the thermal reservoir does not change. It remains constant even though energy can be added or removed by heat transfer. So let's say the energy can be added or removed by heat transfer. So I'm just going to go with the net, or the energy of the entire cycle. So energy can be removed from the thermal reservoir. Energy can be added to the thermal reservoir in the form of heat transfer. What we would obviously, with actual systems, what we see is that when we, let's say, supply heat transfer to a system or a reservoir, the temperature increases as well. Or if we take heat content out of the system, the temperature decreases for that reservoir. But this is an ideal system, and for an ideal system, we can make this assumption that heat transfer is taking place, but the temperature remains constant. And usually there's different systems that we can approximate like this. So for example, if we've got, let's say, a huge system like an ocean, and for an ocean, if we were taking, let's say, heat content out of the ocean in one place, one small place, the overall temperature distribution of the ocean would still remain the same. right? So that is one way to approximate a thermal reservoir. So now we can move on to the statement, the Kelvin-Planck statement. And what the Kelvin-Planck statement says is that it is impossible for any system to operate in a thermodynamic cycle and then deliver a net amount of work to the surroundings while it is receiving energy by heat transfer from a single thermal reservoir. Okay. So what does this mean? That if, let's say, this is the system that we've got, it is impossible for this system to exist if we are transferring heat into the system by just one single thermal reservoir and expecting that we would uh, convert all of this heat into work, right? So what this means is that obviously we would have some kind of losses in here. We should have losses in here. We cannot convert all the energy of a thermal reservoir into work. There needs to be some kind of losses that should be taking place. So in a way, let's say if I had another system over here, another reservoir over here. So if I had a two reservoir system, I'm just gonna build this over here. If I had Q in coming in here and some amount of work takes place, but at the end of the day, I've got some energy that is actually not being converted and it's just being released into the surroundings, which is Q naught. Then this cycle is possible. Okay, so the work done is going to be equal to Q in minus Q out. So obviously this work would be possible, but if I only have a one single thermal reservoir and my system is operating in a thermodynamic cycle, then, so let's say a power cycle here, then that system wouldn't be possible. That is what the Kelvin-Planck statement says. And another way to write the Kelvin-Planck statement in analytical terms is that the work done for a cycle, for a single thermal reservoir, is not going to be positive. So according to the Kelvin-Planck statement, a system undergoing a cycle while it's communicating thermally with a single reservoir cannot deliver a net amount of work to its surroundings. And that means that the net work of the cycle cannot be positive, right? So that is the analytical form of the Kelvin-Planck statement. And the less than sign over here and the equal to sign over here, these are because of the presence or the absence of internal irreversibilities. And we're going to discuss the concept of irreversibilities next. But before we do that, I'm just going to tell you that for a QuasiA statement to hold, the Kelvin-Planck statement needs to hold as well. It's not, if a system fulfills the QuasiA statement but violates the Kelvin-Planck statement, then that system is not possible. If a system fulfills the Kelvin-Planck statement but violates the QuasiA statement, then that system is not possible either. So what that means is that the Clausius and the Kelvin-Planck statements are equivalent to each other, and violating one statement means violating the other statement as well. So we just have to be careful with that. And I'm just going to leave you very quickly with this example of equivalence that is being demonstrated here. So if I have just this one system, this single system that I'm looking at, and from the QuasiA statement, I know that this system alone, this system, is violating the QuasiA statement because I just have heat transfer taking place from a cooler body to a hotter body, and this is the sole effect that is taking place across the system. So this is not possible according to the QuasiA statement. And now, if I look at this system over here, then this system is perfectly fine as an individual system because I've got a thermal reservoir over here that is transferring heat into the system, and work is being carried out, and then some kind of energy is being released to the cold reservoir. So this system is possible. But if, let's say, these two systems were combined together, and this was a boundary chosen now, then would this system still be able to um, take place or do work, let's say? It wouldn't be able to do that because it would be violating the Kelvin Planck statement now. And how would it violate the Kelvin Planck statement? I'm going to leave that to you as a home assignment. Just go and take a look at the system, see why this entire system violates the Kelvin Planck statement. And what that indicates is that because the QuasiA statement is being violated, then the Kelvin Planck statement is going to be violated too. And where the Kelvin Planck statement is violated, the QuasiA statement is violated too. Okay, so just go take a look at that. Both of these statements need to be basically fulfilled in order for a system to be able to do any kind of work.